Hello, everyone. How are we doing today? All right. The plan for today is to continue on with chapter 14. We have two sections left. These sections are concerned with optimization. Okay. One of the most important things that we looked at back in Calculus 1 was if we have some kind of curve, then this curve is going to feature values where it achieves maximal and minimal values. Okay. Now, there are some different situations under which this can occur. For instance, we might have a situation like this, where here we have a maximum value, here we have a minimum value in that region, and then another minimum value down here. And we need to be able to distinguish between these things. Now, when we move to the case of having a surface, things get more complicated. There are more features involved in the objects that we're talking about, and to the point to where it's very difficult to draw useful pictures in enough detail where we can pick at these things out. So I'll probably skip that and use other stuff as we move along here. Okay, so to get things set up, we need to talk about what it is we're working with. So we'll make a definition here. If we have a function f of x, y, it has a local minimum at the point AB if f of xy is less than or equal to f of AB. For all points in a neighborhood of AB. Okay. Remember that a neighborhood would be if AB is this point in the middle, some small disk around AB that has potentially very, very small, but a positive radius. Okay. Um, we call it a local max. If f of xy is instead greater than or equal to f of AB everywhere in a neighborhood. So it's we reverse the direction of the inequality, and it's, or sorry, wait, hold on. Yeah, hold on, wait. Did I write the inequalities in the wrong direction? This is right. Hold on a second. Oh, okay. All right. I now understand my mistake. Sorry about that, everybody. I was only half reading the notes. Yeah. I had I reversed. I did local min first instead of local max, and the thing that I was reading off of did local max first, so the inequalities were pointing in the wrong direction. Okay, so now that we've set things up where we can double check this and fix it, um, so a local minimum, if the function is greater than the value at f of ab everywhere in some neighborhood, okay, and a local maximum if f of ab is the biggest value in that neighborhood. Okay. Now, if we have a local min or max, is the smallest or greatest on the entire domain, it's an absolute minimum or maximum value. Okay, we're familiar with these ideas. There's just some added stuff that we need to be concerned about when we're talking about surfaces. Okay. Now, the next thing that we want to do is be able to find these things, and we hope that it would be the case that we find them in a way that's very similar to what we're familiar with from our previous experience in calculus. Okay, so we'll make a sketch here that's going to motivate the next theorem. We'll draw sort of a hill-shaped surface here. All right, and the max of this function would appear to be up at this point here, right? And in order for that point to be the maximum, what I need to be able to do is draw this intersecting plane here that corresponds to moving in the x direction. Mark our coordinate axes here. Okay, and we also need to be able to talk about moving in the y direction. I'll draw that picture better. Okay, and what this does is it generates the intersection at both of these spots, right? One of them corresponds to this curve. The other one corresponds to this curve along the surface, right? And I know the picture is a little bit cluttered, but both of those curves have a local max simultaneously, right? We see that? Okay, so what this means it must be the case that both of the first partials are equal to 0. Now, there are many, many, many different types of surfaces than the one that I sketched out here, okay? It happens to be the case that f partial x and f partial y both have local mins, or local maxes, pardon me, at the point in question. That is not a requirement. The only requirement is that the first partials are equal to 0. Because in order for the surface to have a local min or max, all of the first partial derivatives have to also have a local min or max along the curves representing the intersecting planes. All right. So let's do an example. So we'll pick f of xy here, x squared plus y squared minus 2x minus 6y plus 14. Okay. What we're interested in is the first partials. Okay. But I do want to point out that it shouldn't be weird to see this if you look at this equation and wonder what it would take to complete the square. Okay, because this would tell us a lot about what this function looks like. So here, we want this to say plus 1, right? It will give us x minus 1 quantity squared just by looking at half of this number squared, right? And then here, we want this to say plus 9. That would be negative 3 squared. Okay, in order to do that, I have to take 10 away from this to move those other values around. Okay, so this tells us something about what's going on with our surface. And from here, we can compute the first partials. It's, of course, easier to differentiate the expanded polynomial. But get used to, when you see an algebraic expression, to, is there a way that I can tinker with this, right? Because this is actually also really easy to compute the partial derivatives of, right? Okay, we can either do it in the term-by-term format given to us by this, in which case we think of this as just 2x minus 2. Okay, or we can do it in the sense of differentiating this and using the chain rule, which is also super easy, because everything else is 0. Differentiate with respect to y, we're going to get 2y minus 6. Okay. Just as easy to differentiate on the other side for the same reasons as the x case. Okay. So what we're interested in is when these partial derivatives are equal to 0. We see that here that means that we have x equals 1 and y equals 3. So we should have, a critical point potentially at 1, 3. So critical points are places where the first partials are equal to 0. Okay. Or if at least one of the partial derivatives doesn't exist, that would also make something a critical point. But that would be a continuity problem or a corner or an edge or something like that, right? Cusp, maybe. Something important happens, a critical feature of the graph here, either a local min or max or some other property. Okay. So looking at our expression here, we know that the critical point's at 1, 3. If we plug 1, 3 into our expression here, which is a lot easier to plug in values to, especially the one that we're looking at, we're going to get 4. Okay. If I plug in any value that's not 1, 3, I'm going to get a number that's bigger than 4. Okay. What that tells me is that I have a local, and it's actually an absolute value here. So if we look at GeoGebra here to see the plot of our function, and we see that that's our point, and we can plot the local minimum here where it goes. 1, 3, 4. We see that it's fine. It is a local minimum, and in due to this particular case, a local or absolute minimum. Pardon me. Yes. Yeah. Okay. So going back to the equation, the way that I was able to puzzle out this was going to be a local min was taking advantage of this other form that I wrote down. Okay. Um, these values are 0 or a positive number because it's something squared, right? So the smallest they can be is 0. They are 0 at 1, 3. X equals 1 and y equals 3. At any other point, I'm going to get a positive number added to 4. So that satisfies the condition that you were asking about in the definition that says I have a local min whenever f is bigger than f of AB, everywhere close to AB. Now, doing it this way is not going to be the most reliable way to determine this, especially for very complicated surfaces. So we want better tools than this, but That's how I did it intuitively in this case. Yes, the absolute comes from the fact that um, we look at the plot and it's obvious. Okay. Also, from the equation, literally every value that I plug in for x, y that's not 1, 3 is going to give me a number bigger than 4, which means that has to be the absolute min. All right. Now, it can also be the case that for problems, we're going to have multiple local mins and maxes. Okay. We'll do an example of that in a second. But first, I want to introduce one of our tools for working through this, and that is the second derivative test. Okay. What we want is a reliable way to determine if things are local mins or maxes without having to do the kinds of guesswork that we were just talking about. Okay. So we're going to suppose okay, so suppose that the second partial derivatives of f exist and are continuous in a neighborhood of AB where the first partials of f at AB are all equal to 0. Okay, so parenthetically, that makes AB a critical point. So we're going to let this expression that the textbook calls D, evaluated at AB, be equal to the second partial derivative evaluated at AB times the second partial with respect to y minus the square of the mixed partials. Huh? The okay, so the theorem is going to revert to the value of D here. This, I mean, it is both an equation and a formula. No. This is where I'm defining what the second derivative test is. So this is a definition, technically. We'll say this definition. All right. So this has a numerical value because I'm plugging in the point AB. There are 3 cases. If the value of D is positive and the second partial with respect to X is positive, then f of AB is a local min. If D is positive and the second partial with respect to X is negative, Then f of AB is a local max. And if D is negative, then our point f of AB fails to be a local maximum or minimum. Okay. So lots to keep track of. Now, a couple things I want to say about this. Number one, you must use this formula as written. In Calculus 1, there was kind of a shortcut for doing the second derivative test, right? If you had the second derivative, all you really cared about was whether it was positive or negative. Okay. Here, we have to be more careful because there's more moving parts. Okay. This is one of those cases where being in only one dimension, as we were in Calc 1, takes away all of the complexity to make it seem like things are easier than they are. Here, what's going on, and this is something that will have a better justification for later, but I can't do it right now. We just don't have the tools yet. We haven't gotten far enough. What D is the determinant of this matrix. So you were asking about the formula. This is the easier way to remember it. Okay, that's where it comes from. There is a coordinate transformation that is being discussed in this expression. I can't do a better job of explaining what that is without going on a huge tangent. But when we talk about integration, we'll get into the kinds of things that's going on here. All right. But what's happening here is that this is encoding information about how the second derivatives of the surface are changing. And we can, from this information, extract, using the second derivative test, whether we're at a local min or local max. There's a question over here. Oh, okay. So I should have written it like this. Thank you. I was not careful enough about writing it that correctly. All right. Now, to answer the second part of your question, no, it doesn't matter because we have Clairaut's theorem. Okay. If a function is continuous enough to have two partial derivatives, then its mixed partials must be equal. Okay. And that extends to higher order derivatives. Okay. So mixed partials should be able to be computed in any order. Okay. So if you have an x and a y next to each other, you should be able to always switch them. So for instance, using the theorem, if I have this should be equal to this. Now, the question is, due to the way that partial derivatives are ordered, this is what this means, right? We differentiate in the order that they're written, okay? Now, this thing over here should be like this, right? Now, Caloros' theorem says that it also has to be equal to this. I should be able to switch the first two because that's a mixed partial, right? So does it matter in what order I differentiate? I can swap as much as I need to, right? As long as I have all the same letters. Okay. All right. Now, let's do an example. We want to look at this one here. X to the fourth plus y to the fourth minus xy plus 1. All right. So we have our expression here. We're not going to complete the square or anything like that this time. We take our first partial. We end up with this, with the f partial x and then f partial y. We're going to get 4y cubed minus 4x. We're very happy that we're only being asked to differentiate polynomials so far. It won't always be like that, so enjoy it while it lasts. But for now, we have some easier stuff. We want these to both be 0. Okay? We can simplify these expressions. Look like this, and we have some stuff to figure out. Okay? This is an algebra problem, all right? Because what I have to do is I have to figure out the set of all values x and y that satisfy this system of equations. Okay? I don't really have a good option beyond probably doing some kind of substitution. I can rearrange this equation here. Or sorry, let's do this one. We can rearrange this equation here, making it look like y equals x cubed. And if I do that, then over here, I end up with x cubed minus x equals 0. So that's x to the 9th minus x equals 0. I factor out an x. Leaves me with x to the 8th power minus 1. This here, I need to recognize as the difference of squares. Because it's x to the 4th power quantity squared minus 1 squared. So that I can write that like this. This one, I'm not going to be able to do anything about. On the left, however, we have another difference of squares. Okay, and then another difference of squares. I know it's probably been a minute, but both of these expressions don't have real roots. X squared plus 1 pretty obviously doesn't have real roots. Its roots are plus or minus I. Okay, and then x to the fourth plus 1 is a similar enough equation that we expect something similar to happen, right? So the roots of this are x equals plus or minus 1 and 0. Okay? Due to the fact that we have plus or minus 1 and 0 here, we go back to this equation, which was the one that we used to do our substitution with, and we need to find our values for y. Fortunately for us, since this is an odd power, negative 1 cubed is negative 1, positive 1 cubed is positive 1, and 0 cubed is 0. So we end up with 0, 0, 1, 1, and negative 1, negative 1 are the critical points. Okay. And by the way, I didn't organize this as well as I possibly could, the way that I'm writing things up here. All right. So I apologize for that. But when you get a little bit out of organized like this, like if I were writing this out for me and not for class, I wouldn't have written this many steps, right? um, when it comes to you writing up stuff for me, I don't expect necessarily this much detail. I expect enough detail for me to be able to look at it and be able to follow your train of thought. Okay. You should write more if you think that you need to communicate to me what's going on. All right. But if what you're doing is correct, it's going to be easier for me to follow along with. Usually, if you write more, it's because something's going sideways. So that's that's the story there. Okay, we have our critical points, and what we need to do is we want to use our second derivative test in order to figure out what's going on with these values. So we need our second partials. We'll put the mixed partial in the middle, I guess. So we differentiate this with respect to x, and then we differentiate it with respect to y. And then lastly, we differentiate this with respect to y. Okay. And we can now plug these into the formula for D. So we get 12 squared, x squared, y squared, so 144 x squared, y squared minus negative 4 quantity squared. So we get negative 16 here. Okay. And then we plug in our three values. We plug in the point 0, 0. We get negative 16. We get a negative value, so it's not a local min or max. If we plug in 1, 1, we're going to get 144 minus 16. It's positive. Okay. And here we plug in -1, -1. Also 144 minus 16, positive. Okay. At both points, the second partial, x's second partial is going to be positive because we're plugging 1 and -1 into this, which has a squared in it. Okay, so that means that these are both local mins. Make sense? But we'll see a graph here in a second. Okay, and then the last thing here to do, and I apologize for running out of space for a problem here, is we want to plug these values into our original function here. So if we plug in f of 1, 1 to see what it looks like here, f of 1, 1 is going to give us a 1, and then -4 plus 1, so it's going to be -1. And if we plug in -1, -1, it's going to be the same thing. Because these raise it to an even power. We get 3 minus signs here, so it's still -4, and then +1. All right, so taking a look at this, we do f of xy again, x to the 4th plus y to the 4th minus 4xy plus 1. And we see that we have this sort of pants shape, okay, with our values for the local minimums here at the bottom of those elements where the sort of pants shape tapers, gets cinched, I guess you could call it, down at the end. And then the other point of interest to us is this point here in the middle, kind of at the center of the pants shape, where we have at the seam a saddle point. Okay. Now, this is the phenomenon that happens when we very likely have, or whenever we have 0 values for the partial derivative, but it fails the second derivative test to being a local min or local max, where we'll have some kind of intersection for our curves that have this sort of behavior. Okay, now it's hard for me to draw, so I'll draw this kind of in the x direction. All right. Think about these pictures on, or think about these curves on the cross section of the shape here. Okay, in one direction, as we kind of move from the direction of our local mins to one another, we see that we have this shape here, right? But if I look at what the cross-section curve would look like if I go in this direction, it's a parabola that kind of opens the other way, right? The parabola in this direction opens down, okay? And then you can kind of see it in the sectioning for the picture here. Here I have a parabola that opens up, all right? But that parabola is perpendicular to the other one, okay? That's the thing that I was trying to draw here. Those are supposed to be perpendicular to one another, okay? That kind of behavior is often what we see whenever we end up with saddle points in our surfaces, okay? And it kind of looks, it, the, one of the ways that it can appear is the sort of pant-shaped picture we have from the example that we were just looking at. And then the other one would be something akin to just a straight saddle itself that you would see on a horse, right? Where you have, I'm a terrible artist. This is gonna be really bad. So you have the front part, and then it curves down like this, and then you have another part that sits here. Okay, the saddle point would be here in the middle, and then this turns up like this. Would be a different type of saddle where the saddle kind of sits. The saddle looks like something you'd sit on, right? Whereas in this shape, we'd have to flip it upside down, which that's not going to let me do. Anyway, so imagine if this were upside down, it would be like a camel's back, right? I'm not an artist. I apologize. I haven't figured it out yet. Okay. So that is most of the story for this section, okay? The next element has to do with absolute minimum and maximum values, okay? We have mentioned the idea that, of course, already that absolute mins and maxes are local mins and maxes that happen to be the smallest or largest value for the entire domain of the function, okay? Now, okay, the key idea here is that a function only has an absolute min or max if its domain is closed, okay? So if we have the domain of a function that is a set that looks like this function will have an absolute min and an absolute max, okay? If I have a function whose domain looks like this, where the boundary of the circle is not part of the domain, then it is not guaranteed that I have an absolute min or absolute max, okay? So closed sets are required here, all right? And also, I have to check the boundary independently of the domain. Calculus only works on the interior, okay? I have to evaluate the boundary independently of that. Okay, and so we'll pick up on this next time, and then also introduce the idea from the final section of this chapter, which is Lagrange multipliers, also related to solving these types of optimization problems.